myself JV and Dr. Kiran Yadav. In this session, I will discuss about Einstein model for the specific heat of solids, which is famously known as Einstein and Debye theory. So let's discuss about the quantum mechanical simple harmonic oscillator first. Quantum mechanical results for a simple harmonic oscillator with classical frequency omega. The energy is quantized using the following formula. En is equals to n plus half h cross omega, where n can have values as 0, 1, 2, 3 and so on. If we draw the energy level diagram, then all the energy levels are equally spaced, and the difference between any two energy levels, the difference between any two conjugate energy levels is equals to h cross omega. Often we consider En as being constructed by adding n excitation quanta of energy h cross omega to the ground state. E0 is the ground state energy of the oscillator, and it is given as half h cross omega. If the system makes a transition from a lower energy level to a higher energy level, it is always true that the change in energy is an integer multiple of h cross omega. During photon absorption or emission, the change in energy, that is delta E, is given as n minus n dash multiplied by h cross omega. In complicated processes such as photons interacting with electrons or photons, it is known as phonons are not conserved. That is, they can be created and destroyed during such interactions. Now let's discuss about thermal energy and lattice vibrations. As we have been discussing in detail, the atoms in a crystal vibrate about their equilibrium positions. The motion produces vibrational waves. The amplitude of this vibrational motion increases as the temperature increases. In a solid, the energy associated with these vibrations is called thermal energy. A knowledge of the thermal energy is fundamental to obtaining and understanding many of the basic properties of solids. A relevant question is, how do we calculate this thermal energy? Also, we would like to know how much thermal energy is available to scatter a conduction electron in a metal or semiconductor. This is important. This scattering contributes to electrical resistance in the material. Most important thought, this thermal energy plays a fundamental role in determining the thermal properties of a solid. A knowledge of how the thermal energy changes with temperature gives an understanding of the heat energy which is necessary to raise the temperature of the material. An important measurable property of a solid is its specific heat or heat capacity. Lattice vibrational contribution to the heat capacity. The thermal energy is the dominant contribution to the heat capacity in most solids. In non-magnetic insulator, it is the only contribution. Some other contributions: conduction electrons in metals and semiconductors, the magnetic ordering in magnetic materials. Calculation of the vibrational contribution to the thermal energy and heat capacity of a solid has two parts: evaluation of the contribution of a single vibrational mode, summation over the frequency distribution of the modes. This is the vibrational specific heats for different solids. Thermal energy and heat capacity. Average energy of a harmonic oscillator and hence of a lattice mode of angular frequency and temperature T, which is denoted by epsilon bar. So this is the energy of an oscillator. So this is the further derivation. And finally, the result that we obtain after this derivation is epsilon bar is equals to half h cross omega plus h cross omega divided by e to the power h cross omega upon kBt minus 1. This is the mean phonon energy. The first term in the above equation is the 0 point energy, as mentioned before, even at 0 degree Kelvin. Atoms vibrate in the crystal and have 0 point energy. This is the minimum energy of the system. The average number of phonons is given by the Bose-Einstein distribution as number of phonons multiplied by energy of phonon is equals to E bar. So this was all about Einstein theory. Thank you so much, students.